Today, electronic calculators are being mass-produced without human intervention. Japan's electronics industry, the world leader, grew from a fierce fight for survival, centering around the production of these new electronic devices. Japan's first electronic calculator was commercially produced in 1964. The following year, output reached some 4,300 units. 15 years later, in 1980, this production mushroomed to over 60 million units yearly. Over the last 27 years, roughly 2,500 electronic calculators have been introduced, an average of 90 new models every year. In peak production years, more than 50 companies, including those manufacturing on a consignment basis, were involved. A large calculator, which once cost 500,000 yen, has shrunk to business card size and now costs less than 1,000 yen. This is a plant that currently produces electronic calculators. The brain of an electronic calculator is a very large-scale integration circuit, or VLSI. This tiny chip contains all the necessary electronic circuits to handle memory, entry, calculation, and display. Automated equipment installs liquid crystal displays on the calculators. It takes only a minute amount of electricity to display figures on screen. The installation of wiring is performed using an electrically conductive ink, which is used to print a wiring system that connects all the components placed onto the plastic sheet. Once a semi-permanent solar battery is attached, the circuits begin to work. A mechanical finger taps the 8 key to confirm the operation of the liquid crystal display. An electronic calculator can now be made by pressing several parts onto a wiring sheet. Since wiring and assembly processes are all automatic, human labor is not required. This is an office equipment exhibition that was held in Tokyo in 1963. The latest calculators of the day are on display, including a new type of cash register that can record several different kinds of sales, and a calculator that can compute complicated square roots. This is a manually operated mechanical calculator. Special gears work together to perform addition, subtraction, multiplication, and division. This is an electrically powered mechanical calculator that uses electric motors to turn the gears. It is a full key system with entry keys from 0 to 9. However, it calculated very slowly, and the machine was very noisy. People who engaged in daily calculation work using equipment such as this longed for a device that could work instantly and quietly. In 1957, Casio Computer Company developed the Casio 14A relay calculator. It had a 10-place display window and a 10-key numeric keypad. This calculator uses 342 electromechanical relay switches. A relay-type calculator developed in America in 1945 used 13,000 relays. It was possible to dramatically cut the number of relays by devising special circuits. The Casio relay calculator was faster and quieter than electrically operated mechanical calculators, which rapidly lost their share of the market to the new relay models. In 1954, television broadcasting began in Japan, and several manufacturers began producing television sets. Around 1955, when public housing began across Japan, electrical appliances such as televisions, washing machines, and refrigerators were gradually becoming common. The number of households with refrigerators had reached 10%. In 1964, the Shinkansen high-speed railway began operation between Tokyo and Osaka. This same year, the Summer Olympics were held in Tokyo, which provided Japan with a chance to demonstrate its economic recovery to the world. The games were broadcast in color and simultaneously transmitted globally via satellite. The age of electronics was blossoming. 1964 was also the year in which 4 firms each introduced an electronic-type desktop calculator. Aleph 0101 was a 10-key machine that could do arithmetical operations to 12 places noiselessly. It cost 800,000 yen. Countless magnetic coils are arrayed inside the calculator. It uses no transistors. The machine was highly reliable, but its high electric consumption made it uneconomical. Sharp then introduced its CS-10A Compet. It was a full key machine capable of arithmetical operations to 20 places. The calculator, which cost 535,000 yen, used a type of vacuum tube called the Nixie tube as a display device. The display tube stood on a base with transistors lined up on both sides. The number of semiconductor devices used was 530 transistors and 2,300 diodes, both made of germanium. Sharp, known at the time as Hayakawa Electric Company, manufactured radio sets before the war. It ventured into the production of televisions as soon as broadcasting began in 1954. Sharp's young engineers frequently spent time drinking with one another after their workday. They discussed what types of products Sharp should produce once the television boom ended. Engineers fresh out of college shared bits and pieces of knowledge they had picked up and gave their ideas on microwave ovens, medical equipment, and computers. Eventually, the top management at Sharp caught wind of their discussions and pondered how these visions could be turned into concrete products.
We had all heard that computers would be a very promising field, especially since computers were the leading edge of technology. But none of us had ever had any experience with them. We never learned about them in school, so we were all beginners. As fate would have it, since I had been the first to mention them, and because I was forever talking about computers, I was ordered to study them.
In April of 1960, 4 young engineers who were assigned to study computers visited Professor Hiroshi Ozaki of Osaka University, a digital calculator specialist. Professor Ozaki had translated Logical Design of Digital Computers by Montgomery Pfister, a world authority on digital calculation. Using this as their textbook, the 4 first learned the basics of calculation theory. Their time for a full year was spent at their university research laboratory. Afterwards, at their office, they would review what they had learned, resolve problems, and prepare their plan for the next day. Finally, after gaining experience with several experimental machines, they began developing a commercial product. Their initial design was based on the direct application of computer theory. It consisted of innumerable panels that filled an area the size of a small room. In order to reduce the machine to desktop size and keep the price reasonable, they had to devise special circuits for calculation. They drew circuits and studied them, only to redraw them again, changing the circuits many times. The circuits drawn on paper were chemically printed on copper sheets, and then parts were soldered onto these one by one. Several hundred sheets were made, and finally these were assembled. The display device was completed by inserting printed circuit boards one by one for each numerical place. The input device was also completed. By pressing the key for 1, 1 appeared on the display. By pressing 2, 2 appeared, and so on.
When we were putting our first electronic calculator together, the calculator was able to only multiply by 1. That's because we didn't have any more circuits prepared. Even so, we had to report to a board meeting about the state of our progress. I remember Mr. Hayakawa, who was the company president then, saying, "Computers are stupider than humans, aren't they?"
Mr. Asada recalls that if management had lacked foresight, their project would have been terminated then and there. Development was not progressing as planned. When they finally thought the machine was capable of calculating, it started making lots of errors shortly after it was switched on. This was because of the way germanium transistors reacted to temperature. With some 500 densely packed transistors discharging heat, the temperature inside the electronic calculator became too high. Moreover, operation at low temperature also was unstable.
We took the calculator into a cold room and watched the machine as the temperature gradually dropped. Then we found that after a while, the signal waves started to act strange. As we continued to check with our testers, we saw irregular waves spread across the circuits. Then we took the calculator into a refrigerated laboratory at Sharp and lowered the lab temperature until it reached minus 17 degrees centigrade. At that point, all the circuits gave out. We realized that it was meaningless to lower the temperature any further. As for the machine's performance at high temperature, we were hoping we could be able to raise the temperature to as high as 60 degrees centigrade. But that proved impossible, because our bodies couldn't handle the heat. We began sweating profusely, and our sweat was dropping onto the machine and causing short circuits.
The Sharp engineers could not use transistors for computers because they were too expensive. They used cheap radio transistors instead and made countless changes to the circuits to improve their performance. With each new change, they took their experimental calculator into cold and hot rooms for testing. Soon, the young engineers began suffering from aches and heart irregularities, though their sacrifice was paying off. The number of calculation errors was steadily decreasing. Reliability could now be maintained. By the spring of 1964, Sharp was poised to manufacture and market an electronic calculator. Casio Computer Company was also in the middle of developing a new relay calculator.
Casio's policy was to try to develop a relay calculator that would surpass the transistorized calculator. The problem was that the circuits for the division function required a lot of hardware. So we decided to build a calculator that somewhat ignored division. We made it. Boy, did we. Casio invited wholesalers to a demonstration of our new relay calculator. All went smoothly when we demonstrated addition, subtraction, and multiplication. But when it came to division, the wholesalers said, "You call that division?"
Even before the calculator finished dividing, spectators were derisively saying, "That's terrible." Several dealers got up and walked out. Management turned pale. Mr. Shimura was stunned.
The new model machine was a flop. The dealers were saying the age of relay calculators was over. The atmosphere was getting tenser, and people were getting up to leave. At that moment, the president said to me, "Find the electronic type that's under development and bring it here." Up to that point, I had been explaining the relay type, but suddenly I was told to fetch the electronic type, which I did. Then the president said, We are also working on this machine. Tell them something about it. Since I knew how a computer works, I began to explain in detail. The dealer's response was enthusiastic.
On a humid summer day in August, engineers set up a makeshift hot room by sealing the room off. Casio had immediately stopped production of the relay calculator. The young technicians had shifted their interest to a transistor-type calculator, which they had been experimenting with on the side. Suddenly, the development of this calculator became a matter of life or death. The men worked as the room temperature soared to above 45 degrees centigrade, drinking lots of water and taking salt to prevent dehydration. The shift from a relay to a transistor-type calculator was proving a grueling task. This is the office of Busicom Corporation in Tokyo. Busicom was influential in the development of electronic calculators in Japan. In 1960, Busicom imported a British vacuum tube desktop calculator called the Anita Mark VIII. Busicom President Yoshio Kojima was then 36.
Since this Anita machine was what we had long been dreaming of, I quickly went to Anita in London. I asked them to sell one, but they turned me down. They said that they would sell me 1,000 units, but not just one. They said if I bought only one, it would mean I was going to copy it. My order was flatly rejected.
This is the Anita Mark IX, which has almost the same function as the Anita Mark VIII. It is a full-key machine that can perform arithmetical operations up to 12 places. It uses Nixie tubes for display and a discharge tube, a kind of vacuum tube, for the switching device. This is the discharge tube, which Anita replaced with a transistor soon afterwards. The Anita Mark VIII sold for 600,000 yen. Japanese companies took it apart and absorbed its technology.
The Anita calculator didn't sell in Japan at all. That's because it was expensive and the performance was poor. But it's certainly clear that it planted a seed among Japanese makers who adapted its technology. Therefore, the honor of having created the world's first desktop electronic calculator definitely belongs to Anita.
In 1966, Busicom marketed its 161 electronic calculator. It offered surprising performance at low cost by using an imported ultra-small core memory technology developed by an Italian firm. The Busicom calculator could make instant computations of arithmetical operations and square roots up to 16 places. It sold for 298,000 yen, memory included. A 14-place Sharp electronic calculator at the time sold for 435,000 yen without a memory. Following Busicom, other firms one after another began to develop electronic calculators based on integrated circuits. Then the competition gradually shifted to the degree of integration. While this was going on, the metal oxide semiconductor, or MOS transistor, appeared. William Shockley of Bell Laboratories invented it. John Bardeen obtained the patent. The MOS transistor could operate on low electrical power, but it could not easily be contaminated by sodium ions. Initially, MOS transistors were considered highly unstable, and the plants that produced them were plagued by problems.
One day our yield was 0. In other words, everything we made was defective. We had horrible periods like that. In the mid-1960s, we were at about that level. You know the feeling of having pains in the stomach when you have a serious crisis? Well, at that time, I felt like my stomach was full of holes. That's because on several occasions, we had nothing to ship out.
The situation in America was no better. Fairchild Semiconductor Corporation of the United States was the world leader in semiconductor technology from the 1960s into the 1970s. Using an oxide film process, Fairchild developed planar technology that protected transistors from contamination. It also invented the integrated circuit. But even Fairchild panicked when production yields at its plants plunged. Fairchild also encountered strange problems when it started producing MOS large-scale integration circuits. The production yields at semiconductor plants frequently dropped sharply when the agricultural spraying season began. Large amounts of sodium contained in fertilizers and agricultural chemicals became ionized and floated in the air. This contaminant made its way into the plants and landed on the wafers. The wafers were also affected after male workers returned from the toilet. Traces of urine on their fingers made the wafers useless. Researchers across America began searching for the cause of MOS-LSI instability. Fairchild gradually traced the problem to sodium. They next devised a method to stabilize the MOS-LSIs by including a small amount of phosphorus in the oxide film. This blocked the action of the sodium. Fairchild immediately announced its discoveries, and the production of MOS-LSIs in America then rapidly improved. In May 1968, Tadashi Sasaki of Sharp Corporation visited semiconductor makers in America and asked them to manufacture MOS-LSIs for electronic calculators, since every Japanese maker had turned him down. Starting with Fairchild on the West Coast, he visited 11 semiconductor makers, including Texas Instruments. They all declined his request after being presented with his massive order and demand for a low price.
The reason was that they placed an importance on profits. Since products for military use were profitable, it was a case of not wanting to do something that produced too little profit at this point. The Japanese concept of securing profits through large-scale production, low markups, and greater sales didn't occur to them. I was being turned down everywhere. The last company I visited was Autonectics, a division of North American Rockwell Corporation. Again, I was turned down.
In despair, Mr. Sasaki made his way to the airport. While waiting to board his flight, he heard his name being called. There was a message from Rockwell. Urgent. Please postpone your return to Japan. 30 minutes later, he returned to Rockwell aboard a helicopter that had been sent for him. The president of the company, in a complete turnabout, agreed to manufacture the MOS-LSIs for electronic calculator use. After a formal contract was signed, Sharp sent Yukihira Yoshida, a young engineer, to Rockwell. He had entered Sharp only 2 years earlier. What awaited him was American technology far in advance of anything in Japan at that time.
All I was given was this one sheet of paper. I had never heard of a four-phase logic circuit before. At first it was total nonsense. I couldn't understand it at all. The most surprising thing was that since we didn't think this way in Japan, it was beyond my ability to comprehend. This was the first technological gap that I encountered. The American engineers wouldn't explain things in detail. They would only answer my questions. They would often use a blackboard to explain their answers. If I appeared to have understood, they would soon erase the blackboard. So I would pretend that I couldn't understand their English, to have enough time to copy the blackboard notes in my memo book. That's how I spent my first days at Rockwell.
In 1969, Apollo 11 took off for the moon. For the first time in history, a man had stood on the surface of the moon and had returned safely to Earth. The key to all this was an ultra-small computer carried on board the spacecraft. The very logic circuits used in this computer were four-phase ratioless MOS circuits, which drove MOS transistors and condensers with 4 types of synchronized signals. Rockwell engineers told Yoshida about it only after Apollo 11 returned successfully to Earth.
生まれました電子そろばん。部下を持ったら欠かせません。計算機の革命マイクロコンペット。
This is the Microcompet 9T8D. Compared to the first Compet that hit the market in 1964, it was 1/6 the weight, 1/3 the thickness, and 1/5 the price. The female workers, all seated in neat lines, are processing wafers. 2 million LSIs in wafer form were airlifted to Japan. Female technicians cut them into chips, attached them to lead frames, and connected them with thin gold wires. A single chip cost $15, or 5,400 yen. Only a few other components were connected to 5 LSIs. The 5 chips cost 27,000 yen. They became the heart of this 98,000 yen electronic calculator that monopolized the market. 400,000 units were sold. It cost 10.8 billion yen to manufacture the chips, which brought Rockwell vast profits as well.
アポロの頭脳エルシーがあなたの手のひらに今着陸。LC8 アポロコンピューターに活躍する LSI を4個使ったキャノーラ L1218 新発売。
計算機は今パーソナル時代シャープ LC 時代。君は遅れていないか。
84,800円。
世界で一番小さいって話があるんですかね。ちょっと失礼。これポケットにも入る世界で一番小さい電子計算機。
手のひらコンピュータービジコンハンディ。
In January 1971, Visicom began marketing a pocket-sized battery-operated 12-place calculator. Its most important feature was that everything was built onto one LSI chip: entry, memory, and calculation. It was the debut of the one-chip electronic calculator.
We were able to complete a one-chip LSI in just 6 months. This was the first time in the world that this was ever done.
This is an electronic calculator put on the market in 1971. It had just 3 parts: a keypad, a fluorescent display tube, and a single LSI chip with polyvinyl chloride wires. This was Texas Instruments' TMS 105. It was possible to complete an electronic calculator by connecting this chip to a keyboard and a display device. This is a list of leading electronic calculator makers at that time. There are 36 firms. Some 20 other smaller firms specializing in consignment production also jostled for a share in the original equipment manufacturer's market. Nearly all used the Texas Instrument chip. The electronic calculator market doubled in size annually until it finally peaked. An 8-place calculator that once sold for 80,000 yen fell to 40,000 yen. In late 1971, design work would begin on the super discount Casio Mini.
We decided on a price of 10,000 yen so that people could use their own money and not their company's money to buy it. But when we thought about what we could make for 10,000 yen, it was a 3-place electronic calculator, something that could only do simple arithmetic. This wouldn't do. Then we thought about a 4-place calculator, and finally a 6-place calculator, which is enough to calculate up to 999,999 yen. But when you consider the users of such a calculator and the purpose for which the calculator would be used, then wouldn't calculating up to 1 million yen be sufficient? Taking this thought one step further, if you're calculating Japanese money, a decimal point isn't really very necessary. So we began developing a 6-place calculator without a decimal point that would do all the arithmetical operations and still sell for 10,000 yen.
A Casio engineer confined himself to a hotel room for 3 days to design a single MOS LSI chip that could operate continuously for 10 hours on a penlight battery and sell at a cost price of 4,500 yen. The design of the logic circuits was completed on December 31st, 1971. The drawings were immediately sent to Hitachi Limited, which secretly produced the LSI chip in 3 months.
Its price was so cheap that at first I had no idea where I might start to redesign so that we could compete with Casio. The price was just too low.
I still remember the television calculator commercial with a catchphrase, "An answer at a touch." It gave me quite a start. Until then, I had been thinking that Japan wouldn't be able to catch up with our firm's technology. But now I thought we had a reasonable chance of selling our products domestically.
9,980円、1万円を割りました。みんなに喜ばれるカシオパーソナルミニ5,800円。答え一発。パーソナルミニ4,800円。
No sooner would you gain consumer confidence and put a new model on the market than another maker would come along and put a more advanced product on the market in a matter of months. The earlier models wouldn't sell at all, no matter how much the makers reduced their prices. This resulted in a common problem that affected all makers of electronic calculators: the burden of unbelievable inventories. Casio and Hitachi were no exceptions.
Innovative technology was required to keep up with the competition for a calculator that was lighter, thinner, and had a longer-lasting battery. One of the answers was liquid crystals.
At the RCA Research Center in Princeton, New Jersey, Dr. Heilmeyer demonstrates a simple application of liquid crystals. Liquid crystals of very regular molecules are inserted between 2 sheets of glass. When a voltage is applied to the entire mass, the refraction index of the light changes, and the glass turns cloudy. If a voltage is applied partially and in a fixed order, it is also possible to create numerals. The secret lies in the special liquid inserted between the sheets of glass.
Sharp's engineers then hit on an idea. Liquid crystals, which emit no light on their own, hardly consume any electricity, and they could be made thin. An engineer immediately flew to the United States to begin a detailed investigation. To find a material suitable for a liquid crystal display, several thousand types of organic substances were tested. Sharp also had to develop new technologies before a liquid crystal display was completed. A capillary sealing method that allowed liquid crystals to seep between the glass sheets, transparent electrodes to drive the sealed liquid crystals, and their fine processing. The research paid off. Sharp is now the world's leader in liquid crystal technology.
シャープ液晶コンペット。電池1本でなんと100時間。白い数字の液晶コンペット。これカサバランカ
LC カード。
2ミリの壁破っちゃってどうしましょう。
The newly developed technology required large-scale production facilities. Advanced firms sought to automate in order to compete with small makers relying on low wages with unmanned production. Printing technology using electrically conductive ink was therefore introduced. Wiring sheets are finished by drawing the wiring diagram on a mimeograph and then printing it on a film with conductive ink. An LSI chip, solar battery, and display device are then pressed onto the film sheet to produce a calculator. The entire process is now computer-controlled and automated. Automation helped consolidate the electronic calculator industry. This forced many firms, however, to withdraw from the market.
This was tragic for all losers of the calculator wars. There were too few winners and too many losers.
With semiconductors, especially ICs and LSIs, the ability to compete is based on the size lots you can make and supply. As you know, semiconductor technology is advancing by giant steps, and the factory equipment investment to mass produce is extremely expensive. Factories have to be refurbished every 3 or 4 years, and it requires an enormous amount of yen to build a new plant. Without the insurance of enough of a demand to repay the equipment investment, the semiconductor industry can't expand. In Japan, because technological development was pushed forward with the support of a large demand, the Japanese semiconductor industry grew. It is this, I think, where the current gap between the Japanese and U.S. semiconductor industries began.
It's not that I can't understand why France and other European nations have come to nervously reject Japanese electronics technology. Not just semiconductors, but various types of other equipment, from facsimiles to copiers. But in the history of Japan's semiconductor industry, all this happened before we knew it. Without anyone paying particular attention to what shape it was taking, there was incredible competition, and in the midst of this frenzy, our rivals disappeared.
High-quality, low-cost LSIs have supported the Japanese electronics industry. The advanced automation now enjoyed by the industry is among the fruits of the calculator wars. An estimated 1 billion electronic calculators have been produced in Japan over the last 27 years, creating vast demand for the semiconductor industry and inspiring its rapid technological innovations.